Let's talk VDML with KJR.
Well, welcome to the next in our series of chats about VDML, validation-driven machine learning, which is our approach to making machine learned products safe and assured. It's really about diving in and verifying and validating what's really in a model and how well it performs under different circumstances, and making sure that the risk profile is properly understood and then mitigated so we can safely deploy. I've got Kelvin with us again, and joining us for the first time is Stan from our Gold Coast team. And today we're going to be talking about baseline validation. And quite often we've talked about this before. It's not so much about building new models from scratch, but deploying models that might exist and then understanding how fit for use and how fit for purpose they are. So the first thing we have to really understand once we've defined our risk profile, and I'll throw to Stan for this because you've been doing a bit of this, how do you understand if an existing model performs? Does it really do what it says on the box? Where do you start from?
Yeah, thanks, Steve. So first, we have a bit of a picture of the business goals and the type of production data we'll be looking at. And once we've identified that, we'll start working on creating a test set, which is what we're going to be using to just validate anything to see if it's fit for purpose. Once we have that test set, we can bring in pre-existing models. It could be a foundation model, could be zero-shot models, and then we can benchmark that on the test set, which we have ground-truthed.
Yeah, so that initial data that you're using, where are you pulling that data from to first get that baseline? Is that a problem you've had to overcome?
Yeah, it's always best to use the data you'll be seeing in production. So it's really good if you have access to whatever recording device that will be used in production. Once we've got that, we can really look at the different variations this model could be deployed in. That could be different angles, could be different lighting conditions, could be different locations. So we do that, we do collect some data of that. And then you pick out some diverse samples, which you then label for ground truth, and that becomes your way of doing initial validations.
Yeah, that sounds really easy, Stan. So surely there's nothing can ever go wrong. Kelvin's never had any bad experiences doing that initial baseline verification.
Is that a throw to me?
That's a throw to you.
Yeah, it is. It's quite tricky knowing where to start, and I think it's always you have to start somewhere, right? So I think the first thing you do is collect some sample data, label that as validation, then apply the model. So probably good to set a case study of what we're talking about. It might be easier for people to follow. So one of the recent models we've been doing is around maritime surveillance. So using drones, looking out over sort of shorelines and out at sea for vessels, and ultimately the context of how that might be used is for marine movements, search and rescue, elements like that. So we've been building a computer vision model around vessel detection and sort of tracking from drones. And so the drones are collecting a lot of video data. So it's a computer vision problem where we're analysing video frames and trying to identify vessels at different ranges and things like that. So, as Stan said, there's plenty of models out there already that will identify boats and vessels and things like that. So your very first context, immediately people see these foundation models and think, well, okay, well, that's a solved problem. We just apply one of these models and see how it works. But again, we've talked before in other sessions about distribution shift is a big challenge. We apply, if this data doesn't look anything like the what's the CV ImageNet data set, if it's quite different to that, then probably the model's not going to work the same if it's trained off ImageNet or COCO or something like that. But anyhow, you've got to start somewhere. So the very first thing you do is collect some sample data, and then, as Stan said, mark up some validation data, and then benchmark exactly where that model performs, how that performs. And typically after you've done that first round, there's a couple of things that can happen. You could say, geez, that model looks really good. Am I ready to put it in production? You need to perhaps ask yourself a few other questions. Or the other typical thing that happens is, oh, that model's not quite performing the way I expect it to. So yeah, the former probably tells you that that first collection of data, that first set of validation, you probably want to now step back after the first pass and think about, is this sort of suitable for the context that we're going to operate? Is our validation broad enough to represent the different contexts? And as Stan said, it might be looking at different lighting conditions, timing, sea states, weather, all those sort of things, different cameras and whatnot. And then the other is, yeah, okay, if we get a baseline that's not good enough, what does that baseline then tell us about other data that we need to train the model, optimize it, and so on, or switching out and comparing different models? So yeah, I might flick it back to you guys, and we can sort of explore those sort of steps a bit further.
Yes, to take us through, Stan. So when you've found a model that looks like it's roughly fit for use, what are the first kind of evaluations you do for performance?
Yep. So first, you'll just identify some of the metrics best suited for your problem. They're different if you're talking about computer vision versus NLP versus tabular data. In our context, looking at computer vision and with the vessel detection problem, we work with something called the precision recall curve. So you really got to understand what metrics you're looking to optimize. Do you care more about catching everything you're interested in and you don't mind about having some false positives in there? Or do you just want to detect with a high confidence what you're looking after? So you first got to set those metrics, those key metrics. Once you've done that, you can get a bit of a broad picture of how well the model performs on your data set as a whole. But as mentioned by Kelvin, you'll often find that the model might perform quite all right in a certain setting, but starts underperforming in diverse other settings. And one thing we've been looking at quite a bit lately is how we can pull in all sorts of telemetry data, all sorts of extra data, talking about the time of day, the location of imaging, altitudes in the drone example, and we can use that to run the same evaluation metrics on subpopulations of that data and identify if there's any underperforming data sets or subsets within that data.
I suppose it still comes back to risk, like you mentioned before. Like, if it's going to perform in certain circumstances, do you want that precision or do you want that that consistency? And how do you go about weighing up the risk? I imagine it's much the same as if you were building a model from scratch or starting an entirely new problem to solve from scratch.
Yeah, so definitely you have to evaluate the context of use and even think about, when you talk about risk, where does that model fit in, say, a human in the loop? You know, how is it cooperating with the human? So a lot of times in this context, if you think about object detection and wanting to detect a vessel, probably your gut feel is you want your recall, like, is it identifying all possible vessels? More often you want sort of a high rate of that, and you're willing to accept maybe a lower rate of precision that it's misidentifying a vessel. And it could be, you know, it could have, you know, 3 false positives for every 1 true positive, because, you know, as a human, you can sort of just discard that, but you might want to make sure it doesn't miss boats that you normally wouldn't see, because the context of, say, doing search and rescue, it turns out that humans are pretty good at dealing with positives, you know, sort of dealing with false positives and true positives, because when we see it, we can confirm it pretty well. But pretty much if we're doing a search and rescue context, is we just don't see it because, you know, we suffer from fatigue and scanning broad areas and things like that. So how do we team with the machine learning model to have more of that attention for looking for potential objects? So again, you know, you'd sit there and look at your metrics and think about, how might I balance that out for that context and sort of change my expectation. But but also, you know, a bit down to what's that context of the operational use. You know, if you know, we've got a vessel, again, you need to think about the size of the objects we're detecting in the image. So, you know, if there's something that's like on the horizon 30 kilometers away and it's 2 pixels high in the image, are we expecting the computer vision algorithm to identify that? Or is it something that's got to be within a certain distance and recognizable as a vessel? You know, what's those operational characteristics that you're translating the model to as a performance characteristic of how it's going to perform from a real world scenario? And you know, pretty much these object detection models are known to have problems with like small objects. So how do we perhaps deal with those sort of known challenges when things are much closer and occupying like a full frame? It's pretty easy to tell something's a vessel. But yeah, when it's like, you know, a total area of 6 pixels or something like 2 by 3, it's pretty hard, you know, for even a human to be able to do that. And the other thing is, you know, what's that reasonable, when we say we baseline as the first step, well, what is the human baseline? Because, you know, the reality is that the recall of a human is probably only 30% in that sort of context of doing that analysis in a search and rescue context. So it doesn't imply it has to be 100%. But it's just like a significant uplift on the human performing that activity.
So on that problem and going from, you know, detection at a very long distance under suboptimal atmospheric conditions, where you're talking about a few pixels here or there, how do you go about that consultation with a subject matter expert or that domain expert? From, it's a long way sometimes, or a long mental way, from the lab where you're experimenting to how do we solve this problem in the real world, and what does that context look like? Can you tell me about some of the experiences you've had dealing with subject matter experts to try and establish ground truth in that operational context?
Might be over to you for that one, Stan. What's your views on it?
Yes, certainly. So I'm probably more on that side of the machine learning engineer and the data science side of things. And what I find is you're a bit isolated. I guess you're a bit away from where the actual action happens. So over iterating over different models, we've learned to really start talking more to those stakeholders and really, working together, solving these problems. So looking at validating a model, and rather than just looking at these data science metrics, asking how useful this is to the stakeholder. And that's where you often find out that the metric you've set at the start might not have been the correct metric. So with the VDML approach, we're focusing much more now on just really understanding that business case and just like the agile approach, just having a lot of input during the development of these models.
It's also that subject matter expertise that you're really encoding the model as well, right? Like you'd think something like a vessel detection would be something straightforward. We all sort of know what a boat looks like, right? Or at least that's what you think you would think. And we know other problems we've looked at. You know, if we're like Stan and I work on a cardiology application looking at echoes of videos of hearts, and you know, next minute you're talking to a cardiologist and it's only the cardiologist that can tell you that part of the heart that you're supposed to be drawing a sort of a bounding box around or an outline of, and gets really tricky around that, what that ground truthing is. But even something as simple as a boat, we all think we know what a boat is, right? But what we've found is that you get all these sort of corner cases, which requires that interpretation. So, you know, we look out and there's a beach and we want vessels, you know, if we're doing it from a safety point of view, like a search and rescue or a monitoring thing, you know, there's heaps of people on stand-up paddle boards, right? And we go, okay, they're vessels. But when we, you know, when you do the objects, you're sort of saying there's two parts of it. I want to detect the object, but also want to indicate what the boundary of the object is. How do I mark that out? Because that's a key part of the metric about identifying, you know, the boundaries of things. And so you go, oh, the person on a stand-up paddleboard, are they part of the vessel, or the people in the vessel? Or we've got images of dredgers and they've got big boom gates, and is that part of the vessel or is that not part of the vessel? Is a vessel parked up on the sand or on a jetty moored up? Is that identified? You know, what are these sort of subject, you know, these business analysis type things? And again, this is the challenge with machine learning. It's, you know, the specification is the sort of examples that you're coding up as your ground truth, right? So, but these are all things that you've got to sit down and evaluate. What do you know, do I want people to classify all the stand-up paddle boards and the surfboards and you know, people are water skiing and they're towing a little inflatable dinghy behind it? Is that a vessel? You know, do I want those identified? It's quite tricky.
Yeah, it's interesting. There's lots of aspects of boats ain't boats. I understand it's sometimes hard to tell the heading of a boat as well. Do we need to know the direction the boat is traveling in? Is that part of our objectives that we're trying to solve? And then we're thinking about things like wake trails or which direction it's pointing compared to a whole bunch of other factors. And that could also influence your collector as well. Given the data sets you're working with, it might even be hard to train or fine-tune a model if you don't have enough data of boats moving in a direction or stationary boats. Or as you said, boats on the shore. Do we count boats on the shore or towed boats? What other types of considerations, like what are the errors that you come across most in that computer vision initial model baselining? What are the typical kinds of errors you see, Stan?
Yeah, usually the most unexpected ones. So often once you deploy run a model on a data set which it hasn't been trained on, you'll notice that clouds get detected as boats. There's all these things in the background. Might be just a patch of grass, might be some reflection of the sun on the water, triggering the model to detect boats. So it's often, yeah, just especially when baselining this model, it's the unexpected. And that's what you then want to correct as well. If you know we'll see a lot of this type of data, maybe I can still use this baseline model and just fine tune it by removing those false positives if that's what I'm after. Maybe I'm not, as Kelvin mentioned, maybe I'm just interested in recall and I can get away with those false positives and might be quite happy with the performance of my model.
Yeah, and you pretty much have to come down to that error analysis. I think what happens is we do all this stratification of, you know, small objects, large objects, and things like that, and you generate these aggregate sort of precision recall statistics, right, for each of the categories. And it's easy to get lost in what that means. You more or less have to go into those errors and sort of draw out the error class of it. It could be a whole bunch of things being classified as clouds, or buildings where the tops of buildings overlap the sea and it kind of looks like the top of a boat sitting at the sea. So, you know, how do we sort of identify those classes of errors that are continually coming up and look at how we might, you know, fine tune the model or correct those errors next iteration around. But that error classification stage is sort of like a key element to go through. After your validation's done and you've got your aggregate statistics, you really need to step down and look at your first of all, your error classes are your false positives, your false negatives, and then look at each of those and try to break it down into, you know, what is that kind of error that might have triggered that and how we might optimize the model in the next phase.
Yeah, we also found that rather than just trying to label as much as possible this data, sometimes it just helps to run inference over a bunch of videos and just visually inspect where those failure cases are.
Mm. Yeah.
Is there a distinct difference in the models and the way you treat those baseline models for computer vision when we talk about time series versus still imagery?
Yeah, no, that's definitely something we're starting to see a lot more because we're mainly dealing with these as time series videos. You can sort of look at an individual frame and sort of do your classification on that. But if you look at the frame going across, you might see the object appear and then disappear. And you sort of want to almost treat a segment of an image and look at that and saying, do we take an object that it's appeared, you know, at least X number of times in that sort of frame. And Stan and I were just today looking at another problem of that, of could we actually, because the videos, this other example we talked about in an earlier episode, feral animal management, as you fly over, in the thermal image, the object sort of hides, that might be buried in the grass or something, and then it appears again, and then, but it's still in that track, but it's sort of appearing and disappearing, and an element of almost drawing an interpolation across that of where we think the image is. And because you have a bunch of aspects in that computer vision thing, is it's not just, there's a couple of variables that impact whether we consider an object detected or not. And in that metric is there's the IOU bit, which is the intersection over union, about, okay, we draw a bounding box and we've got of what the ground truth is and the bounding box of what we're detecting. Is there significant enough overlap for us to say, yeah, they agree on the same object? So there's that sort of precision of the outline, and then there's the confidence of the score that the model detected it. And you'd set a threshold typically and say, like, let's say 50%. If it's above 50% confidence, we say it's found it or not. And so oftentimes you play around with those values and decide what you want to have. It might be you consider objects detected maybe at 25% or something like that for sparse objects. So there's a little bit of sort of parameter tuning across those sort of examples to see what the optimal is for the, if we want to up the recall, we might want to push that metric up and just deal with more false positives sort of thing and sort of cancel those out.
Yeah, having worked on the Feral AI project a little bit and done some of the data collection, it really does make a difference when you're watching the video as a human versus looking at the still images of the thermal. One of the particular cases, I believe they talked about it, or they may have talked about it in the other episode, is where a kangaroo's been lying down for a period of time and then gets up and moves. The thermal imprint of the kangaroo on the ground, do you count 2 kangaroos? But clearly on the computer vision, you can see it's gotten up and it's moved, hopped away.
Yeah, you can see it.
But we can see 2 imprints of roughly the same temperature because at night, there's a very distinct difference between the ground and a kangaroo.
Yeah. But it sort of tells you that the data collection is quite key to that as well, right? Like consistently, the problem that you're applying your machine learning to, you sort of want a more narrow context about the data that it's looking at. So a bit like if you're expecting, this thing to work with every possible camera, whether it's CCTV versus a drone versus something else, I think it's almost impossible to have a foundation model that is going to work in all contexts. You sort of want to say, how do we narrow down this model to a particular context? It might be this particular drone doing maritime surveillance, or it might be we're really good at doing the feral animal stuff and it's flying at a height of 45 meters. And that's sort of optimal to detecting certain types of animals, where if it's at 100 meters, it's probably not going to work that well because all the objects are too small, sort of thing, right? And you just know your model doesn't perform with that form of data collection that well.
So given all these challenges, I'll throw out this hypothetical question or this discussion question. And it's probably controversial because you quickly know the answer. But given all the challenges for the problem you're trying to solve with maritime, reconnaissance, if there's no real off-the-shelf model you can pick, do you still see an advantage to tuning and experimenting with off-the-shelf models and then working from that baseline, even though there are a lot of pitfalls in terms of the data it's trained on, the domain shifts, the stratifications maybe not right against the parameters that we see, the characteristics that we're measuring against, compared to building something from scratch, like in the case of Feral AI, where we built the annotator by scratch. Do you think that there is a case for building it from scratch? You can both have a for and against, if you like. It's a discussion.
I'll let you understand.
Yeah. Okay. In computer vision, we often start from a pre-trained model either way in an object detection setting that's often pre-trained on a core data set. And the reason why we do this is because we would need vast amounts of data and GPU compute just to teach the model these high-level features. What are colors? What are edges? All that sort of things. And that's transferable to most computer vision problems, I'm going to say. There's probably a case for certain data that looks completely different to do train from scratch, but often you do start from that pre-trained model. So if you would pick a pre-trained model that's already optimized for something similar that you're trying to do, I don't see much of a downside to it. And yeah, we can either use it to fine tune, or we can decide, hey, let's label some of the data. Let's use it to label all our images that haven't been touched by a human annotator, and then have the human correcting them rather than starting from scratch.
Yeah, no, I agree entirely with Stan. I think it's not just computer vision, but you look at the large language models. I think the foundational models are great. They've actually accelerated what we can apply things to, like the previous iterations, pre-trained models was, labeling tens of thousands of examples. But I think where we're at is still really application around narrow applications, because the context of what you're applying it to, we just don't know what the performance is going to be like in that scenario. So by narrowing it down, we can actually better understand its performance and its characteristics and know how that system is going to operate, reasonably consistently. If it's a very open domain, and this is sort of the discussion we see with the large language models, with very few, like zero-shot, few-shot learning, they look quite exciting, but you just know the open-ended questions that people could ask, you could end up in a rabbit hole really easily, right? So I think where they're going to be most applied is where they narrow down the application. They can almost use a language model to say, hey, this doesn't belong into the sets of questions you can ask me, because I just say I'm not going to be able to respond to that in a meaningful way, or even to vet the output as valid and not full of profanities or stuff like that. But the same in computer vision, we sort of narrow it and we really fine tune the performance to because what we're saying in the narrow domain, we've really constrained the distribution of data that we're looking at, and we sort of understand and we've evaluated how it performs across that sort of scenario.
So when we talk about those narrow applications, Kelvin, we're talking about having to use really specific data sets, and the management of that data set is paramount to the success of the fine tuning, would you say?
Yeah. I mean, the whole premise of machine learning, it's data centric, right? So data is central to everything we do. So, like the first step, baselining, is collecting your validation data. Here's the examples I'm going to run through a foundation model, but I need my validation so I know how it performs. And then if it doesn't perform, then you're thinking about what's all the training examples I need to build up to actually optimize it or feed it. But then even on the validation side, like we've discussed, there's lots of other permutations that you need to evaluate. And, even there there's some, going out and finding some of that real world data can be quite tricky, a bit. And we were just chatting earlier this week about like in a search and rescue context with boats. Okay, part of it might be later we want to detect a boat in distress. So there's smoke or fire or a flare coming up. It's not going to be cheap to collect that data, right? And it doesn't occur that often. You sort of want to know it's going to work. So how do I go and get that data? And I think some of the things that I'm starting to think about as well is how do we augment data, not just from a training point of view, but from a validation point of view as well. How do we generate images of those real like rare occurrence corner cases that are super important to the model, like detecting a boat on fire or something like that. And I think, some of it we're starting to look at simulators, for instance, to generate that data, because the beauty of the simulator is you can then start constructing all these scenarios programmatically. The only challenge then is, does my simulation data look like the real world data? And then how do I put those two together? So, but that's definitely a path, I think, that for high performing dependable models, ultimately a route that you need to go down, because the cost of finding the real world data is quite expensive.
Absolutely.
And also how can we tie in that human in the loop after deployment to basically mention that or notify that this was a missed case and that this could be added to a training set to avoid missing it going forward.
And then back to your concept, Steve, is then that concept of the data store is key, because as you iterate and build this validation of models, they're not one-off tests. It's sort of like your data store is your repository of your data, and that's how you've labeled your test sets and your different variations. You identify your training data and demonstrate how that's separate from your test data. And then, that tells you over time, if I keep testing and refining my model, eventually my test data starts getting a bit tainted. So then I need to move to a new set of test data to validate that the system's still performing. So the whole way along through that life cycle, you really want your data store as being that repository for your examples, your test data, what you're collecting from the real world, what you're synthesizing, what you're augmenting, and you're building that up, annotating it, adding metadata in so that you can sort of track that evolution of the sort of the validation and the optimization cycles that you're going through.
Yeah, excellent. I think that might be our 30 minutes, fellas. We've had a great chat. Any final thoughts on starting with a baseline, of starting the journey of baseline validation of a foundation model? Any key takeaways, tips for young players?
Test early.
Test early.
Be clear on your metrics. Be clear on what you're trying to solve.
Absolutely. Clarity is key, and understanding the context, I guess, is making sure you don't just read what's on the box and say, oh, that's my problem too. There's always going to be specific nuance to your context. Fantastic. Great chatting with you all, and we'll chat again soon.
Yep. Thanks, Steve. Thanks, Dan.
Thanks, Steve. Thanks, Kelvin.